Okay, good afternoon, everybody, and on behalf of the committee for the colloquia of the department, it's my pleasure to invite you to the last colloquium of this academic year, and this is a very special occasion. It's the last, and we are lucky to have a very distinguished speaker. The subject of the talk of today is Higgs and Neutrinos, portal to the future of particle physics. So we will be hearing about particle physics, and we are lucky to have a leading figure in the field that is playing a very, very relevant role to shape the future of particle physics. So it's my pleasure to introduce today's speaker, Professor Yifang Wang. Professor Wang got his PhD actually in Italy at the University of Florence, right? So he also speaks some Italian, but of course the colloquium will be in English. And Professor Wang has worked in the L3 experiments at LEP at CERN. And then for those of you like me who have been in the field for long enough, you may remember in 2012 when Diabay measured the angle, the last missing angle of a neutrino mixing matrix by the Diabay experiment. He was leading the experiment. And this great result was what gave Professor Wang a series of important prizes, including the Breakthrough Prize and several others. Professor Wang has been also the director of the Institute for High Energy Physics in Beijing. I was lucky enough to spend a month there, so it was a really interesting visit for me. And at the moment, he's the spokesperson of the JUNO experiment. I will not say anything more about the JUNO experiment because I'm sure we will hear about JUNO today. And he's also playing a very active role in the so-called CEPC Future Collider, something else we will hear about today. I already listed some of the impressive achievements that Professor Wang managed to achieve during his career. These also include memberships in prestigious academies such as the US National Academy of Sciences, the Royal Society, and many others. So I would really like to thank you for accepting our invitation. It's a pleasure to have you here. I'm looking forward to your colloquium, and please welcome Professor Wang.
Thanks very much for the invitation. It's really a great pleasure for me to come back to Padova. I think we had many discussions 7 to 10 years ago for the design of the JUNO, and then now we see it is come to a realization. So it's really my great pleasure to come back. So today I'm going to talk about what we have been done in the past 10, 20 years about the Higgs and neutrinos. So I think everybody knows about this standard model of particle physics. We have matter, quarks, and leptons. We have intermediate bosons, and then we have this Higgs, which actually is the origin of all the mass. And in the process, there were many, many Nobel Prizes. So this was actually a great success in the past, let's say, 70 years. And we see there are more than 20 Nobel Prizes for this great success. And a lot of young people were asking if this is the end of particle physics, because all the particles predicted by the standard model has been discovered. And young people also question whether there are any opportunities for them. So, however, standard model, although a great success, there are still many, let's say, clouds over the successful model, and there are also experimental evidence that the standard model is not perfect. So we know that neutrino has a mass, and also we see many of the several sigmas of the deviation from the standard model. Theoretically, we still have issues which we don't know very well. For example, the meta-stability of the vacuum, let's say the flavor symmetry between the leptons and the quarks, which seems to indicate there are some symmetries even deeper from the current lepton and the quark level. And also, we have to understand where the origin of the Higgs mass and the huge mass difference between the elementary particles and fine-tuning of parameters, and also the dark matter CP evaluations, which we are not able to give sufficient information and explanation to the universe issues. So standard model is indeed just an effective theory up to 0.1 to 1 TeV. So there must be something new beyond this energy scale. So if you look at what could happen for the future of particle physics, there are, generally speaking, the three main directions. One is the constituent of matter. We try to understand the elementary particles and try to see if there are any deeper level of the another new, let's say, particle or particle level, particle world. And another direction is the interaction of particles. We try to understand the grand unification, the Higgs particle itself, and also many other tests of the standard model. In addition, we have a very close connection with the universe. We have to understand the cosmology, which give us a lot of questions, and also they are actually pose challenges to particle physics. So along these three main, let's say, directions, we have two portals for solving these problems. One is the Higgs, because Higgs was is a particle which was discovered the latest, and it has a very close connection with the electroweak symmetry of the universe, the early days of universe, and also the phase transition and matter-antimatter symmetry, naturalness, and indeed, it should be a bridge to the dark matter, because dark matter has only the property of mass, and Higgs was giving the mass to the visible world, and whether there's a connection behind through Higgs is a question mark. But if you look at all the existing particles in the standard model, probably Higgs has the closest and the most probable connection to the dark world. So indeed, for these problems, so there was an international consensus that a Higgs factory is actually the highest priority for the future of particle physics. And there were many proposals, including one in China, CEPC, Circular Collider at CERN, and also linear colliders in Japan and also at CERN. So there are 4 different types of Higgs factories in the world, and the circular colliders have higher luminosity, and it can have the underground tunnel reused for the PP collider. But the linear collider actually is also very important. It gives the only way to go higher energy, let's say 1 TeV or even higher, 3 or even 10. So indeed, we do need both technologies and both directions. But at this moment, there are different pros and cons as a Higgs factory. So CEPC had a very high luminosity, that's very similar to FCC, which is almost factor of 8 more than linear collider. And the cost, at least in China, is less than in the case of SCC, and also even less than the linear collider. The starting time for the construction could be earlier in China, but all the other factories probably need something like another 8 years to start with. In addition, there are many other options. In the United States, you have the C-cube, and people talking about the energy recovery LINAC. And also, there's a proposal to use plasma-weak acceleration to have the asymmetric Higgs factory, the proposal called half. And also, nowadays, in the United States, also at CERN, people talking about muon colliders. So it is a very active field, and at this moment, we are having this symposium in Venice to talk about the future. So all these kind of options are on the table, and we have to see which one is, has the best chance and which one is actually the best for our future of the field. If you have linear colliders, you don't have to really worry about the optimization of the lens and so on. You just do what you can do, and in the future you can upgrade, make it longer and higher the energy. But for circular collider, you cannot change it afterwards. You have to really optimize the circumference. So in this right plot, we did the optimization to see what is the best, say, circumference for, say, the cost per Higgs, including the cost of construction and also the cost of the operation. You can see from this plot that the minimum is at 80 kilometers. So it shows that in order to balance the construction cost, operation cost, electricity, and also in particular to overcome synchronizing radiation, 80 kilometers is the best, let's say, circumference. And if you take into account, for example, the future of the PP collider, indeed 100 kilometers is probably the best because it can give you more room for high energy where you want to have a PP collider. So that's the reason why we end up this 90 kilometers for the FCC and 100 kilometers of CEPC. And if you really in shortage of money, let's say, for the construction, indeed you can actually go down to, let's say, 60. It's not something not acceptable. It can be done. So let me give you some introduction about what had happened in China. Indeed, since 2005, we have been talking about the future of our next high-energy physics machines. We had a Beijing Electron-Positron Collider operated since 1988 and was upgraded in the year of 2009. And we think that the machine is going to be a small temporary machines, and we have to think about what can be done in the future. So we didn't find a solution in the year of 2005 until the discovery of the Higgs. We realized that indeed the Higgs factory is the best choice, or at least one of the best choice for our future of particle physics. And the idea of CEPC came out exactly the year of 2012. And we also came up with the idea that only Higgs factory is not sufficient or not warrant for the construction of such a large science facility. And we proposed that we could have a proton collider afterwards in the same tunnel, very much like LEP and HC. And this was actually the first idea for the Higgs factory to have a proton machine afterwards. And we proposed this at the October workshop in Fermilab for the future of the Higgs factory. So these are the references there. And indeed, this idea was quickly spread out all over the world, and it gained momentum in China and also in the world. So starting from 2012, and then we prepare for our kickoff meeting in 2013. We started the kickoff of the project, and in 2015, we had a very preliminary study, and then in 2018, we finished the conceptual design report, and in 2023, we finished a technical design report. So we studied physics, what we can do with such a machine. So in summary, indeed, such a machine with a very high luminosity can improve the Higgs couplings by almost a factor of 10 comparing to what could be achieved by high Lumi HC. And you can do a direct measurement or direct search for the new physics up to 10 TeV, which is also about a factor of 10 higher than what can be achieved by the high Lumi HC. You can also do many of the electroweak measurements with the improvement more than, say, factor few. Some are less, as factor of 3, some are more, as factor of 10. So we summarized all these studies in a few white papers. The first one was Higgs physics. You can see it was published in 2019. And we have flavor physics, which just published beginning of this year. And also another new physics searches at the beginning of this year. So we are actually working on the other two white papers, electroweak physics and also the QCD. So indeed, Higgs is the portal to new physics. You can see from the plot. It can do the dark matter searches. It can study the electroweak phase transition to exclude many of the, let's say, different models. You can see the coverage of CEPC is actually quite sufficient for all the parameter space, and also searches of the new physics and different branch ratio sensitivities and so on. So I'm not going through the details, and indeed you can see it is very effective machine for new physics. So the machine has been designed in the last 10 years with some iterations, and the final parameters is the following. It's a 100-kilometer circumference. We are going to guarantee the compatibility of the future proton machine in the terminal for the electron machine first. And the synchronous radiation power is going to be 30 megawatt initially, and can be upgraded to 50 megawatt. You can also upgrade the luminosity for the Z, and also can upgrade the energy for the TT bar. And the machine is designed in such a way that you can switch different energies at any given moment. You can, starting from the Higgs, going down to Z, going up to the top, and also going to the W and so on. So you can switch back and forth at any given moment. And this was the design of this switching bypass scheme. This was actually invention, let's say, I don't remember exactly, but probably 6-7 years ago during our study. And indeed, this was actually very interesting features, and now also the scheme for the FCC. This machine is not only a machine for particle physics, it can also generate a lot of synchronous radiations with very high energy. So you can see from the bottom left figure, the flux and also the energy of the synchronous radiation from this machine, comparing to many of the dedicated machines in the world. So you can see that they actually exceeding most of the machines, dedicated machines for gamma rays, except LCAS2, so which is, let's say, slightly less the energy, but the flux is actually quite high. So you can see that this is actually a multi-purpose machine for particle physics, also for nuclear physics, for material science, and so on. So as I said before, we finished the technical design report in the year of 2023 and published in the year of 2024. The design, the TDR had roughly 1,000 authors and about 1,000 pages. So you see this is a big document of international collaboration, and most important figures people are interested are the cost of this machine. So the summary table here shows that the total is about 5 billion euro, in which, let's say, slightly less than 1/3 for civil construction, a bit more than 50% is for the accelerator, and the rest is for detector and also for contingency. The machine was designed not just based on paper or on the simulation, based on our experience at the high energy photon source, just completed construction in Beijing, and also our 40 years of experience on the Beijing Electron-Positron Collider. So this 6 GeV light source is actually one of the most advanced light sources in the world. We just finished construction this year And by end of this year, beginning of next year, it's going to be open for general public for users. And you can see the LINAC, the storage ring, and also the magnet alignment, the vacuum, and so on. And many of these equipment are actually more advanced than the need of CEPC. So indeed, this is a very good practice and test of the technologies we have for the future CEPC. And you can also see from bottom right, our BPC have been running stably at the beam current of 900 milliamps and with a stable luminosity of 1 × 10⁻33. This is a very advanced storage rings, and it shows that we can run this kind of machines with a very high current. And this was actually one of the biggest challenges we have for the future circular colliders. So in the past 10 years, we have been working on the equipment technologies for this circular collider. And you can see that we went through almost all the equipment listed on the right column. You can see that the fraction is the fraction of the cost. So the biggest cost is the magnet and the vacuum. And then you see the going down from IF, mechanics, and so on. We managed to finish most of this equipment test, and the specifications has been met with a few exceptions. So these few exceptions, we're still working on the prototyping, and we believe that in the next, say, 2 years or so, we should be able to finish. So our next step is to finish a so-called engineering design report with a number of issues to study, mostly for the mass production readiness. We have a long list, 35 working groups. I'm not going through all the details, just give you a few examples. So the first one is superconducting cavities and modules. So during the TDR phase, we finished both the collider ring SR cavities and also the booster cavities. One is 650 megahertz, another one is 1.3 gigahertz. For 1.3 gigahertz, we finished the complete full modules. You see from this picture, you see how big, how long it is. This is one complete full module. But for the 650, it's a short module. So we had to finish during the EDR with this 11 meters long cryo modules containing 6 two-cell cavities. Construction has been started. We believe we should be finished very soon. And the second example is the high-efficiency clastrons. So during TDR phase, we finished CW mode 800 kilowatt klystron, which reached the efficiency of 78%. Currently, the world level and the most advanced level is less than 65%. So we already achieved the highest efficiency for the klystron. But we believe this is not the end, and we could actually improve further. We did a study using so-called energy recovering technique to improve the efficiency. The test stand showed that we can achieve efficiency of 88%. So right now, we are going to build one full klystron module so that we can improve the efficiency further from 78% up to more than 85%. So this is going to save us a lot of cost for the electricity. So this is extremely important kind of technique we have to accomplish. The third example is automatic production for the magnet. Even in China, we worry about the labor cost for the magnet production with a quantity of 15,000 magnets only for the booster dipole. We also have storage rings and also many other kind of magnets. It's a single largest system we have to worry about. So the cost saving is extremely important. So we came up with the idea to design and manufacture automatic production line for the magnet. And in this case, we can make it work 24 hours a day and 7 days a week. And we estimated that we can reduce the cost by 30 to 50%. We are also working on technologies for the future. The most interesting one is the plasma accelerator as a driver, as a very important technology for the future. And we believe that we can use CEPC as an injector to drive this technology development in China. And we came up with a conceptual design, and it seems okay, but we need the experimental proof. So we modified the BPC2 LINAC to be a dedicated test facility to testing technologies like cascading, like a positron acceleration, and also electron gun, laser, and so on, this kind of equipment. So funding has been available, and I think in the next 2 or 3 years, we can probably have some very interesting results coming from this testing facility. We're also working on the future proton machines. The key technology is the magnet. And to reduce the cost and to increase the magnetic field, we have to use high TC kind of new materials. There are 2 possibilities. One is Rebico, another one is iron-based materials. And we believe the future actually should be rely on the iron-based because it's a metal, it's cheap, isotropic, and has a very advanced kind of features. So you can see that from the bottom 2 figures, we made the world's first iron-based superconducting coils, and we tested in a 24 Tesla magnetic field. It showed that you can maintain the current. And this is going to be the future technologies, and we have been working on with partners to have the cable itself, and also hopefully in not too far future to have the mid-scale cable production. You can see starting from 2016, we managed to improve the current capabilities, and comparing to the final, let's say the goal, we are still missing a factor 2 or 3, and we believe that in the next few years, we should be able to achieve this. For the detector, we came up with the concept, which starting from the vertex, we have vertex detector, the tracker, the calorimeter, and so on. They're all very similar to the standard kind of detector, but with the 3 new kind of ideas. First one is that we managed to have this silicon tracker plus time projection chamber so that you have precision tracking and also particle ID. So in this case, you get both using this kind of combination of technologies. And in the tracker is just maps HV CMOS pixel detector. And auto tracker is AC LGAD kind of new technologies. So you can actually have a measurement both timing and the position. And for the electromagnetic calorimeter, we use crystals. And for HCAL, we use glass scintillators. I'm going to have a little bit of a detailed explanation for this. For the electromagnetic calorimeter, the traditional kind of technologies are either you have very good energy resolution or you have the position resolution, but you cannot have both. To solve this problem, to have both energy and the position resolution so that you can have a good particle flow algorithm implemented. So we came up with this idea to have the crystal arranged in an XY direction, and then the beam comes in a perpendicular way so that the Z position or beam direction is measured from the layer, number of layers. So by doing this, we using software to resolve the ambiguity problem, and we can actually get very good position resolution. You see that we can distinguish diff showers at the level of 30 millimeters, which is just roughly the factor 2 size of the crystal cross-section. And energy resolution can be at level of 1.3 50% over square D. This is almost factor 10 better than silicon tungsten kind of EM calorimeter. And for hadron calorimeter, we came up with the idea of a high density glass scintillator, which is cheaper, but very good resolution compared to, let's say, plastic scintillator. And the fact that you can only build, manufacture small glass pieces actually perfectly matching with the requirement of the PFA. So in this case, you make small pieces of glass, and then you have very good kind of software reconstruction to get good energy and position resolution. And you can see that from our simulation, it shows very good performance. 30% over square D is roughly factor 2 better than typical hadron calorimeter. And the light yield we have been achieved is about 1,500 photoelectrons per MeV. And this is almost factor 10 better than, you can see here, this is a previous kind of glass light output at the density of 6 grams per cubic centimeter. So having this kind of high density, high light yield glass scintillator, we can build best hadron calorimeter people ever have been built up to now. So the CEPC has a planning showing here. We finished the TDR. We are working on the EDR, which is going to finish at 2027. And then the start construction will be something like hopefully 2027. So we plan to submit a proposal to the central government within the 15th five-year plan. And we already had a review by the Chinese Academy of Sciences. It was #1 in the hydrogen physics, nuclear physics, and the #2 for the basic science. So I think we have a very good chance to go through the CAS and then all the way up to the central government for the construction. So now let me move to neutrinos. This is also, I mean, everybody knows that this is a very important portal for the physics of the future. And indeed, for neutrino studies, mass is its most critical issue. And up to now, most of the studies are concentrated on the understanding of its mass. And the neutrino oscillation, indeed, is the most sensible way to probe the neutrino mass. And the idea of the oscillation came from Pontecorvo, where you can see that the formula indicate that if there's a mass difference, and the neutrino could happen to have oscillation. And where you need two parameters. One is the oscillation amplitude using the parameter called theta, and also another one is oscillation frequency, which is determined by the mass square difference. You write down the three flavors of neutrinos, and the mixing matrix is 3 by 3, this kind of matrix, where you have 6 independent parameters. In the past, from atom effect neutrinos and the solar neutrinos, the 3 parameters and another one half have been measured. So theta 23, theta 12, delta M 23, and delta M 12 are all measured. And theta 13 was measured in our diabatic experiment. And the unknown parameters are the mass hierarchy, or the sign of the delta M square, and also the CP phase. So our JUNO experiment is actually a continuation of our liquid scintillator and the react neutrino experiment. We try to put our detector at the baseline of 60 kilometers from reactor. And at this place, you can actually do a very good, let's say, mass hierarchy measurement. The idea came out in the year of 2008, and the construction started 2015, and we are going to start data taking mid of this year. The detector was put at 60 kilometers from the reactor, so you can imagine that the distance made you a lot more difficult to have enough neutrino events. So you see that because of this baseline, the detector has a much higher, much larger the target mass. JUNO is almost factor 20 larger than ChemLand. And because of the size of the detector, the light produced by neutrino event has to be able to come out from the liquid scintillator being detected by the phototube. So the light yield is another problem, and typically more difficult even than, the larger detector, much more difficult than a small detector. So you can see that we need this light yield from JUNO almost factor 4 larger than ChemLand. This is another kind of challenge we have. So the JUNO collaboration is established around the year of 2014, and this is after the project approved by Chinese government 2013, and many of the other countries approved the project afterwards. So we have now about 700 members from 72 institutions in 17 countries, regions. You can see clearly from this table, there are many Italian groups. In particular, Padova is a main player of this project. So this is the civil construction. You can see our portal on surface. This is from this slope tunnel. And then we have another one at the vertical shaft. So we have 2 access for safety reasons. And underground, you see the tunnel and also the big experimental hall. So we designed the detector for 20 kilotons, I just mentioned before, and it was built underground in a cavern of 50 meters diameter, and the cavern also has to be 70 meters high. The aquatic tank holds 20 kilotons liquid scintillator, and its diameter of 35 meters. So it's roughly 12 stories a building. So it's a big kind of structure made of 260 pieces of acrylic panels. And we thermally form them into a spherical shape and then bond them together. So you can see how it was constructed. We start from a steel structure, and then in the middle we have a platform, so that on platform we can have people standing on it, and also acrylic panels were arranged and then bound together to form a spherical shape. So these are kind of shape you can see we built from the bottom on top steel structure, and then from top to bottom the acrylic sphere. This is what we have finished, the PMTs, the radar electronics. In total, we have 20,000 phototubes, 20-inch, and also another 25,000 3-inch phototubes. They came from Hamamatsu and NNVT, which is a company from China. And you see the picture of the phototube when it's finished. This is the detector which has been more or less finished. From the top, you see phototube for the VTOL and the water pool. And the bottom, you see people actually almost about have finished the TIVAC installation. And we happily make a picture at the bottom of the detector. One of the major issues is how to make everything clear, and then you can fill the sphere with a liquid scintillator. We have to control the dust in the liquid scintillator at a level less than 8 milligrams per 20 kilotons. So you can imagine 8 milligrams, how little it is, and to make sure it can be satisfy our requirement for the radioactivity. So we made a design in addition to all the other purifications for liquid scintillator, we had to make sure that the tank, the acrylic tank, during the installation has to be cleaned. So we came up with the idea that after we finish the construction of acrylic, we wash the acrylic tank, and then we fill the liquid scintillator. As you can see that this is a diameter of 17 meters of sprinklers, and then you have a high pressure water to wash completely the inner surface for almost 10 days, and make sure that the water coming out from this surface of acrylic is clean enough, and we know that everything is up to our specification. And then we start to fill the liquid, the water into the acrylic tank, and also, of course, outside. And then we replace the water by the liquid scintillator. So by doing this, we can guarantee the cleanness of the liquid scintillator. So once we finish everything, so we start to fill the detector. First of all, we fill in and out of the acrylic tank by water. Our total amount is about 60 kilotons, and we have to guarantee the transparency, the particle count, resistivity, and in particular, uranium thorium purity. So it has to be controlled at the level of 10 to minus 15 gram per gram. And then we had to worry about the stability and the engineering safety of the structure, because the acrylic structure is only 12 centimeters over 12 stories of building, so structure itself is very fragile. During the feeding of the water, the temperature change and also the water level change could easily destroy the structure of the acrylic. So we had to make sure that the pressure in and out is exactly same. So but in addition to that, we had to make sure that the air does not go into our acrylic sphere, because radon is going to destroy the radio purity requirement for the detector. So we made the arrangement that the air during the feeding, because we have liquid in, the air had to go out. They go out from the top, and from the side, we have a nitrogen tank, so they suck the nitrogen and they push air out. So in this case, we can maintain the pressure equilibrium and also maintain the cleanness. And to monitor the stability, we have a lot of sensors installed on supporting bars, and we have the measurement, the simulation to see whether supporting stress on these bars are equivalent to what we have been calculated and agree with our expectation. So you can see that during the feeding, the stress actually changes. Some are flat, some change dramatically, and this indeed actually very much inconsistent with our simulation. It shows that at different places, at every given moment, we have a simulation, we check whether the stress is in consistence with our calculation or with our design. So we successfully filled the structure with water, and everything is safe, and the cleanness has been maintained. And you can see from water tank of detector, I mean, you see when you turn on the phototube, you see this muons. The detector shows that the detector works. And then we have to fill the liquid scintillator. So first of all, you have to make the liquid scintillator clean. We have a storage tank of the linear alkali benzene, which is the raw materials of the liquid scintillator. And then you have to purify with aluminum oxide to remove particles. And also you have distillation to remove radioactive impurities. And then we have a mixing to add the PPO and the bis and B. And then you go to the underground system, which is water extraction system and also gas stripping system. They remove further the radioactive purities, and also the radon and the oxygen, and then you load the liquid into the detector. So this is how it looked like. We finished the filling of more than 2/3 into the tank. We have remaining something like a few thousand cubic meters of liquid scintillate to be filled, which we believe it takes us another 2 months to finish. And we measure the quality of this liquid scintillator. We measure the transparency by the UVVS every day, every batch. Attenuation length, up to now, by sampling, we measure to be about 20 meters. And the radio purity by ACPMS to be less than 10 to minus 16. We do it every week. And also, we look at the radon and others. So up to now, before we load the liquid, everything up to our specification. And then we measure what has been inside the detector once it's been loaded. First of all, we have to see whether our PMT works or not. So we have a total of 17,000 PMTs looking inward to the central detector. And up to now, we have only 10 dead PMTs, including electronics. So you see that the inefficiency or dead rate is only much less than 1%. And we have another, let's say, 1%-ish of PMTs, which are not so stable. It has some small flashes, and we have to remove them. And you can see a very good waveform for typical PMTs. Single photoelectron has a very good waveform, thanks to very nice PMTs and also very nice electronics, which was made here at Padova. And you can see that the noise is only 5% of single PE, which is never heard of, I think, in the past for electronics at such kind of low level of the noise. We also measured the radon level in the liquid scintillator, much less than 1 millibecquerel per cubic meter, and also the uranium thorium, which is less than 10 to minus 16. So the final goal was 10 to minus 17, and we believe that we are not very far from there. The reason we couldn't give a number because we still have to wait some time that the radon decay out and look at the remaining uranium thorium in our liquid scintillator. So everything now looks fine. We have the sufficient light yield. We believe that energy resolution is very close to what we have been designed for. All of this very much depend on the large PMTs. So the electronics was designed here, Padova, and produced together with IHEP in China and installed there. So you see the specifications, many of them are very, very unique. This is also the first time that we put electronic box underwater, which requires that electronics box has to be very, very reliable. You cannot modify it, you cannot repair it, and the dead weight required is less than 0.5% per 6 years. This is a very stringent requirement, and in the end, it works perfect fine. So I cannot resist not to showing this video. You have better understanding how it looks like. So you see, this is surface. We're building our surface facilities in 2015. And then we started digging. And during digging, we end up a lot of problems with the water. You see a huge amount of water coming out. And it made us quite of delays of the civil construction. And it was not so easy to build this. And you see these steel bars. This is to reinforce the structure of the rock. It is 30 meters long. They were injected, they were put into the rock to make sure that the rock itself is in the end is stable, that they are not going to fall off. And you see from the picture how big the size, you feel how small a person in this large underground hall. And once we finish this concrete structure of the water pool, we start the installation of the detectors. The first one is steel structure. You see, once they were manufactured in the factory, they are installed on site from bottom up. And then we have this middle platform, which can move up and down, change the diameter so that you can install the acrylic structure. And the platform was also used for the construction of the steel structure. And this is acrylic. In the factory, they were working on the study how to make them. We have special production lines for acrylic so that background is factor of 10 or maybe more, less than a normal acrylic. So we managed to have this very low background acrylic, and they have to be cleaned and so on, and then be installed there. Installation of the acrylic was a major challenge we had, and we had met number of problems, but in the end, we managed to solve them, and they have been installed finally successfully in the site. This is about we have finished. This is the bottom chimney. We are about to install it. And you can see how the platform moves. And the PMT, I didn't talk very much about it. This is actually domestic made 20-inch PMTs with higher collection and quantum efficiency comparing to Hamamatsu. So this is also extremely important for our energy resolution. And then you had to install them, and the people have to find place to stand. So this was also a major concern, how to install PMTs, where people stand. So anyway, we found the solution, and we managed to install all the PMTs. The clearance between PMTs are 3 millimeters. This was the, okay, you see the electronics. And you are going to see familiar faces. This test was done here in Padova with underwater by 40 meters of water. And you see this is 3-inch PMTs. You see someone you know. Yeah, this is a liquid scintillator system. You see everything is more or less fit exactly the space we had in the ground. This is also a way to minimize the excavation and just fit what is needed to minimize or optimize the cost. It's a water system. And this is top tracker. This is mostly the contribution by French. And then we start the water feeding. You see the water comes out from the camera. Yeah, this is how simulation, how it look like a neutrino event in our detector. So last slides about physics. So JUNO by itself can determine the mass hierarchy by at the level of 4 sigma in 6 years, 3 sigma, 6 years, independent of CP phase. And the neutrino oscillation parameters can be measured to a level less than 1%, you see here, almost factor 10 improvement over the past measurement. And also can do the supernova studies diffusion supernova neutrinos, geoneutrinos, and also solar neutrinos. You can see the comparison of the JUNO performance with Bolexino. So indeed, for Britney 7 PEP, we can do much better job than Bolexino. And for CNO, if our background is at level 10 to minus 17, we can do better than Bolexino. So indeed, I just showed you before, the background is less than 10 to minus 16, so very close to 10 to minus 17. So we believe that we can do a very good job on solar neutrinos. We have a near detector. This is also another major contribution from Italy and from INFN. So this is a near detector to measure a reference energy spectrum from reactor. And this is a very good energy resolution of 1.5% over square root E. Another factor of 2, 3 better than JUNO. We use the very new technologies of second PM so that we can achieve this unprecedented energy resolution by using a liquid scintillator. Indeed, JUNO is not going to be stopped only at the mass hierarchy. It can also be upgraded to a double beta decay experiment. You can see from the bottom table, indeed, this is 20 kiloton detector. If you load up 1% of the isotopes, it's 100 or 200 tons. So you can easily get tens of tons or 100 tons of isotopes in your detector, and you can achieve, indeed, a very good sensitivity to neutrinoless double beta decays. Indeed, compared to all the designed experiment, we have actually almost the best sensitivity to the future of neutrinoless double beta decays. So this is a summary. So we started from diabase to JUNO, and started from BPC 200 meters to CEPC 100 kilometers. Indeed, this is a great achievement in the past 40 years, and we believe that we can move further with these two very important facilities in international collaboration manner. So thanks very much for the listening. Thank you.
Thank you. Thank you very much. And now we have time for some questions from the audience. Yeah.
Thank you very much and congratulations. I was wondering the much reduced cost of your collider electron-positron, sorry. Is it mainly driven by the fact that it will be built in China, or also is it related to some specific choice or idea, let's say?
The civil construction cost in China is roughly a factor of 5 or 6 less than in Switzerland. Secondly, the geology. I mean, this factor of 5, 6 is not just because of labor cost. It's because one of the big factor also is the geology, because we choose a very good geology in China, and it's granite, and you use much less concrete and steel to maintain a good stability of your structure. So that's, of course, plus the cost, labor cost in China. So you end up this factor of 6. And the machine is only 50% cheaper, and this for many, many reasons. And the rest is not much different.
Okay, we have another question.
Yes, thank you for this presentation. No, I was wondering, you mentioned that JUNO can just by itself reach a 4 sigma precision on the ordering of neutrinos in about 6 years. No, I was wondering since there are already other experiments on neutrino oscillations, in particular, referring to NOVA and T2K. Do you plan to combine, say, your results to have a kind of coordinated approach with NOVA T2K to reach this level of precision on the ordering in a shorter time? Or do you think that maybe this road that you indicated is preferable at the moment?
We will certainly have combined analysis at the very end. But I think at the very beginning, we're going to have independent measurement first. And then we try to use information from everybody, let's say the atom square 3.2 and theta 1.3 to have combined fit. And then afterwards, we try to understand in detail systematics and have a combined analysis with NOVA plus T2K. Yeah, with 3 steps.
Okay, we have time for another question if there is any.
So it's more a... Really? Okay, so in the meantime, I saw that you have a kind of a scheme in which maybe you have, is it different detectors for different physics, like top, anti-top, X, W? Yeah, you showed something like a bypass scheme.
Yeah, bypass
mean that you have more detectors?
Detector. No.
Ah, no, okay.
Detect is one. Yeah. And detect has been designed to have 6 lambda for hadron current emitter plus 1 lambda for EM, so total 7 sigma. In this case, it is good enough also for total, because it's very hard to change a detector afterwards.
What is the basic idea under this bypass?
The bypass is for beams with different energy, and they need different RF cavities. So you give them, you give it, you see the RF cavities, your Z, H, and TD bar, they use different number of cavities to get different boost of RF to the beam.
I see, I understood.
Because sometimes with different energy, different beam current, and so on, you need different type of cavity. And we don't want to, every time, to move out the old cavity, move in a new cavity, which requires months or even years of operation. You have this bypass scheme, so you don't have to touch them. They just go different ways, so that you can go in back and forth to run the machine at any desired energy.
Thanks.
So how do you see the outcome of the European strategy process influencing the decision on building the China collider?
At this moment, if everything goes on well with the schedule, I think there's no impact for Chinese, let's say, planning for the near future. Of course, if we failed, and we have to see the next 5 years plan, then of course it's going to be affected substantially by the European strategy.
How do you see the possible international involvement in experimentation at the CEPC?
Well, we certainly want to have international collaboration, and this is actually a major feature of CEPC, distinguishable from other Chinese projects in competition with us for the funding. So we hope that we have something like 10 to 30% of international contributions to the CEPC. All involved, yeah? Both, yeah.
Okay, I don't see any other raised hands, so the colloquia, the season of colloquia ends here. We are already working for the next seasons that will start in October. It will be announced soon, so keep an eye on the email and on the social media. And it's my pleasure to thank Professor Wang again.
Thank you.